another video for the seismic design of structures, and I'm going to talk today in this video about different points. Only I'm going to explain about some hints or explain some concepts that is important in seismic provisions in ASCE 7 in general. So I'm going to talk about the basic requirements for design, like 4 main basic requirements. And then I'm going to talk about the redundancy. And after that, I'm going to talk about the deflection amplification factor and what is the importance of it. And then the overstrength and why we use overstrength and what is the main reason or cause for the overstrength. And then I'm going to talk about response modification factor and why we are reducing the seismic demand and what is the main role of response modification factor. Okay, now let's go to the basic requirements directly. So here actually we have like 4 different basic requirements. So we have 1, 2, 3, and 4. They are considered to be the most important or the profound or fundamental requirements for the seismic design. So first of all, we need to select gravity and seismic force resisting systems appropriate to the anticipated intensity of ground shaking depending on the SDC, which is the seismic design category that we have explained in the previous videos. So we need to what? Select gravity and seismic force resisting system or lateral seismic force resisting system. 2 systems that needs to be selected well, and we need to think about the anticipated intensity of our earthquake. So based on this, we can design the structure, or we can secure that our seismic design is going to be reliable. Number 2, lay out these systems to produce a continuous, and this is very, very important word, continuous, regular, and redundant load path. Again, continuous, regular, and redundant. What is the meaning of these 3 words? Continuous means that there is no interruption, that the lateral load resisting system, or even for the gravity, it is common for the gravity actually to do so. We understand it very well, that we need all the columns to receive the load from the upper columns and safely transmit it to the foundation. And also from the secondary beams, the secondary beams to the main beams, to the girders and to the columns, and then to the foundation, right? This is commonly what we do for gravity loadings. It's the same here for the seismic force resisting system, that we need to have a continuous. So there is a continuity in the lateral force resisting system should be maintained in order to say that this is, or this layout is going to be reliable. And number 2, regular, means that we should, whenever that we have a plan, for example, our force resisting system, lateral force resisting system, should be regular. If we're going to put here shear wall, for example, then we need to put here shear wall with the same strength, for example. But if I'm going to put another part here, shear wall here, and another column here, for example, then I increase the strength here, but actually the center of rigidity has been shifted to this point. Okay, and this means that our system, my layout is not regular. Okay, so this is the number 2 requirement. The third one is redundant load path, so that the structures act as integral units in responding to ground shaking. What is the meaning of redundant? Redundant, if you have taken the class or the course of indeterminate structure, the more redundancy in the structure means that the more alternate or alternative load path for the load to go through in order to transmit the load from one element to another. Okay, so redundancy means that different load path. Whenever there is one element is going to fail, we are going to find alternate load path and another element going to receive and transmit the load safely. So this is the meaning of redundant load path. Okay, we are going to control each one of them using some factors as we are going to see shortly. so that the structure act as integral units in responding to ground shaking. Integral units. Integral means that all units are connected together. Okay. And number 3, analyze. So after selecting, after laying out, then we are going to make the analysis, right? So analyze a mathematical model of the structure subjected to lateral seismic motions and gravity forces. These are the forces that we are going to design and analyze our structure with. Lateral seismic motions and gravity forces. And number 4, proportion members and connections to have adequate lateral and vertical strength and stiffness. So we need to proportion, which is the design stage. This is the design stage. We need to design our members and the connections. So members and connection means that all these structural elements to have adequate lateral and vertical. So lateral and, of course, definitely vertical. What? 2 things, strength and stiffness. So this is the 4 design steps, or we can say the main basic steps for the seismic design: selection, laying out our plans, and then analyzing, and then proportioning, or the design stage. Okay. Now let's go and give some hints about this, about what we have explained. A basic assumption that the earthquake loading can come from any direction. This is an important assumption, that whenever we have a plan, we are not sure from where the earthquake would strike and attack. Commonly, we are looking to one direction in an orthogonal direction, which is X and Y, and say that maybe it come here and we can analyze in this direction and this direction, or something like this. But actually, the angle of attack of the earthquake, the strike of the earthquake, we're not sure from where it comes. So this is an important issue. A basic assumption that the earthquake loading can come from any direction, and this is why we are going to check our structure for different load cases, and the load combination should consider different load directions. Okay. Another important hint is vertical ground motion is not analyzed. Take care of this. Not analyzed, but it is taken into consideration approximately by adjusting the load factors for sorry, this is a mistake, for load up and down. So this means that whenever that we have a vertical component for our structure coming from the earthquake, if this is the earthquake, we have a vertical component and horizontal one. The vertical component is not going to be considered in analysis, except for rare cases and special cases. We are going to consider it. When we are near fault, for example, or seismic design category E and F, we need to consider the seismic design with the analysis of the vertical component. But in common, generally, we're not going to take it into consideration in analysis. Rather, we are going to take it into consideration for load factors when we are going to take the load combinations, as we are going to explain in the next video. So this is going to be considered approximately in our design, or the design load combination, not in the analysis. Okay, so this is the second assumption. You can say that they are assumption hints. You can put it them like whatever that you want, but they are going to be an important hints or assumptions for our design. Reduced response spectrum is used as representative of earthquake. Do you remember when we said that we have response spectrum and smooth response spectrum? So we are going to use this, but we are going to reduce it. It might be reduced, okay, in some way or another, as we are going to say, as we are going to see, to to get what we call it the inelastic response spectrum. So this earthquake that is going to be used, there is reduced response spectrum is going to be representative for the earthquake. What is the reason for this? Because there is some damping is going to be introduced for our structure that we are not taking it into consideration. The original response spectrum, it is supposedly to be elastic, but actually the structure is going to exert and dissipate some hysteretic energy during the earthquake course. So this means that there are some kind of dissipation of energy, and there is some additional damping that we need to take it into consideration when we are designing our structure. So this is why we are reducing the response spectrum. Another thing is, as a result of this, the maximum considered earthquake level of ground shaking, okay, so the maximum considered earthquake risk targeted, as we said, structural elements are expected to yield or buckle or otherwise behave inelastically. So it might be yield or buckle or behave inelastically. Why? Because we are expecting hysteretic energy dissipation. So this means that hysteretic energy dissipation by yielding and buckling and so on, okay, these are going to be used, or it is going to be represented through the reduction of the response spectrum, Based on previous practice that ductile, regular, continuous systems behaved well, because these systems, that is ductile, regular, and continuous systems, they behaved well, the response modification factor, that we're going to talk about it shortly, is used to reduce elastic forces, and so the elastic forces coming from the earthquake is going to be used or going to be reduced through R, which is the response modification factor. Is used to reduce the elastic forces, all the elastic forces, and the MCR, the maximum considered earthquake, is going to be multiplied by 2/3, which is reduced by 1/3. Why we are doing so? Because our experience from the previous systems, they behaved what? Well. We found by experience that whenever we design our structures to be ductile and regular and maintaining continuous load path, we found them they behaved very well during the previous earthquakes. Based on this, we tried to reduce the seismic demand by the concept of response modification factor to take into consideration the hysteretic dissipated energy, and we are going to multiply the maximum considered earthquake by 2/3, means that we're going to reduce it by 1/3. Remember that I have mentioned about this 2 videos, I think, before, and I mentioned the rationale behind the 2/3. So that the rationale that we are going to obtain after the reduction, we are going to have 1.5 safety factor. Okay, if you do not understand this point well, please revisit the previous 2 videos and you're going to understand it. Okay, these are the hints. Now let's go directly to the one of the important things, which is the deflection amplification factor. Okay. Actually, before discussing anything, we need to draw an important graph, which we call it inelastic force deformation curve. What is the meaning of this curve? It is a relation between the lateral seismic force on the vertical axis, we call it V, and in the horizontal axis it is representing lateral deflection drift, which is the drift. Okay, so if the building is going to move, okay, if we have the building in this way and then it moves in this way, then there is a kind of deflection delta, and there is a base shear that is going to be developed. If we are, this is the inertia force, so the base shear should be in the opposite direction. Let me put it like this. Okay. So we have like force deformation relationship, and this curve is a very famous and common curve for any structure. We call it the pushover curve. Okay. Now we need to think about what is happening for this pushover curve and what are the controlling points. Actually, in the elastic stage, we are going to find that structure is behaving elastically until reaching one point. This point, its deflection, we call it delta S, which is the drift under design forces. This is where that we are designing our structure. It's in the elastic range, as you can see it here. The corresponding base shear is going to be Vs. So Vs here is going to be corresponding to delta S. What is the meaning of S? Design. This is the design. And elastic. This is what the code is providing for us. I mean that the ELF, the equivalent lateral force method, is providing for us. But the structure itself does not stop here at this point. If you increase the loads on the structure, okay, you're going to find that it goes into this behavior. There is some behavior until it reaches to one stage which is important. We call it VY, the fully yielded strength. The structure is going to deform non-linearly, and plastic hinges are going to deform, okay? And these successive yield hinges is going to push the structure to be into the nonlinear range until it reaches to the full maximum strength. We call it fully yielded strength, the maximum strength. And after that, the structure would start to drop the loading, dropping the load. Okay? Okay, so now this is what the structure is going to behave, actual behavior. But when you started the design, this elastic line, if we consider that our structure is going to behave unlimitedly elastic, then it will go with this dashed line. Actually, this is theoretical. This would not happen in the reality, just we are imagining this. Okay? This is the elastic response of the structure, which will not happen. Okay? Okay. We found something that is very nice. Okay, so now let's assume about the response modification factor. In our design and analysis, we found that the level of base shear gives us delta S, but the actual displacement in the structure is going to be larger. It is going to be here, for example. It is going to be delta D, the design drift. Okay, this is the drift under design forces. This is design forces, which is coming from the equivalent lateral force, the force that we are having in the structure, okay, CS times W, if you remember, okay? So the corresponding one is going to be this drift under design forces. But actually the design, or we can say the actual drifts that would take place, it is larger. There is inelastic behavior would take place. So in this case, we are going to find that the real displacement is going to be here, let's say. Okay? So there is a difference between the delta S and the delta D. So what is the difference? This difference we can assume it to be CD, which is the displacement amplification factor. So actually we are going to amplify the drift under the design forces by CD in order to obtain the drift or the design drift. Okay? So from where we can get this CD? Who can tell this to us? The professionals. The design experience that we have had before in the previous design and detailing of earthquakes. For each structure we are going to have, there is a specific CD for each design, or for each lateral load resisting system we're going to find CD. For example, this is what already the code is giving for us in table 12.2-1. You're going to find here the seismic force resisting system. We have many of them here in the left hand side or in the first column, and you are going to find here response modification factor, and there is overstrength factor, and here deflection amplification factor. Right? So this is our concern. This is the CD. This is CD. As you can see here, for different resisting systems, you're going to find it is like different values. Look here, 5, sometimes 4, sometimes 1.5, sometimes 1/4, or 1.25, and so on. So they are totally different. Why? What is the reason? Who says this 5 and 4 and 2 from where? From the experience, from design and previous experience. Okay? Okay, that's good. Now we understood what is the meaning of the amplification. Okay, the amplification displacement factor. Okay? Okay, I'm going to revisit this again when I'm going to talk about the response modification factor and the overstrength factor. So remember this curve very well, because I'm going to revisit it shortly. Okay. Now, for the inelastic deformation, this is only writing what I have explained. The elastic deformations calculated under these reduced design forces are multiplied by deflection amplification factor CD to estimate the deformation likely to result from the design ground motion. So this is the ground motion forces is going to give us this. Okay, it is going to give us actually the design ground motion is going to give us displacement higher than this one. This is the inelastic displacement, okay, not corresponding to this one. The amplified deformations are used to assess story drifts and to determine seismic demands on elements, okay, of the structure that are not part of the seismic force resisting system and on non-structure components within the structure. So why we need this kind of delta D design? For two reasons, or for many reasons, but there are two important reasons among them. These amplified deformation, they are going to be necessary for story drifts. Story drift, we need to know the story drift, okay? And to determine the seismic demands on elements of the structure that are not part of the seismic force resisting system. If we have structure, okay, and we have like columns that is part of the lateral resisting system, okay, example, something like this. If we have another like another bay that is only having gravity frame, so only it has gravity beams and girders, so actually the total structure is going to be deformed laterally with delta. It will go in this direction, right? So this means that this system, which is a gravity load system, is going to experience this delta, which is delta D. It is going to experience delta D. So we need to design it. We want to know how much delta is going to be experienced. If we're going to analyze for B delta effect, for example, so we need this delta, the real delta, not the drift under the design forces. We need the real delta. What the structure is going to behave, how it would behave in reality. Okay. And in something else, in non-structured components within the structure. In non-structured components, we need also to know what is the delta. Whether that the non-structured components are going to withstand this delta or not. So it's important for us to know about this. It's important for us to know about this. Where CD is substantially less than R, the system is considered to have damping greater than the nominal 5% of critical damping. Typically, we use 5% for concrete structures, but actually the structure can show that it has more damping than this. Okay. Now, let's go to the overstrength and understand what is the meaning of overstrength. Okay. So, what is the meaning of overstrength? Before anything, we should go and revisit this figure again. Do you remember this level, which is VS, the design base shear, here? And do you remember this level, which is VY, or the maximum fully yielded strength that the structure would provide? The difference between them, we call it this ratio between VY and VS, we call it omega. This is what we call it the overstrength. What is the physical meaning of overstrength? It means that the design forces that we have designed our structure with is not the ultimate maximum strength of the structure. It is only a portion of it. So as you can see here, almost it is more than double, right? This is VY, almost double VS. This means that this overstrength factor is huge. When you design your structure for 100 kilonewton lateral force, the structure can resist almost 300 kilonewton. So this is huge. Yes, this is huge. Because we are expecting this. The codes are designed for this. Designed for to design at the elastic range and let the remaining nonlinear range to be experienced. Okay, and we are going to use this overstrength factor, okay, for design in some cases. So the difference between the two, it is going to be, as I said, the difference between the two, it is going to provide the omega, which is the overstrength factor. The overstrength factor. Okay, now let's go back to the overstrength and read it again. The structure overstrength described earlier results from the development of sequential plastic hinging. So yes, that's right, because we are having plastic hinges is going to be provided, as we said in the previous, as we have seen in the previous figure, in a properly designed redundant structure. So the successive sequential plastic hinging is very important. Take care of this word, which is sequential. Okay, it's not simultaneous. Take care of this. We want the plastic hinging to be sequential. That is going to start to accumulate or start to spread around the structure, okay, in a sequential way, so that we lengthen the time for our nonlinear range. But if they are going to be accumulated simultaneously in one particular place, there is a failure mechanism would take place. So this word is very important and key word here. So it should be sequential and redundant. And redundant structure means that different load baths are going to be there. Several other sources will further increase the source of overstrength. For example, firstly, material overstrength. Actual material strengths higher than the nominal material strengths specified in design. That's very true. May increase the structure overstrength significantly. For example, it is known that the mean yield strength of A36 steel is about 30% to 40% higher than the minimum specified strengths used in the design calculation. This is right. So for A36 steel, for example, we use the yield strength less than almost 30 or 40%. Okay, so this is steel is about 30 or 40. The yield strength is about 30 or 40% higher than the minimum specified strengths that we are using. So this means that the material itself, if we are using steel, is going to be higher than what we have designed based on. Okay, another source is going to be, second, member design. Member design strengths usually incorporate a strength reduction factor or resistance. Do you remember phi? This strength reduction factor, 0.9 for tension, for example, 0.7 or 0.75 for other types like fracture or something like this. This is what is the meaning? That we are reducing the strength of the material, but actually the material would behave maybe higher than this to produce a low probability of failure under design loading. So it is probability nature that we are taking into consideration, but reality, I mean that deterministically, no need. I mean that it is maybe not right. Maybe the strength reduction factor 0.9 or 0.7 is not right. Maybe it's only like we need to reduce by 5% or something like this. Not by 10% or 30%. The third is the designers themselves. You are providing a kind of overstrength for the structure by yourself. You are introducing additional overstrengths by selecting sections or specifying reinforcing patterns that exceed those required by the computation. Similar situations occur where prospective minimum control the design. That's right. That whenever that as designer, you are always, whenever that the requirement of steel is, area steel is 10 centimeters squared, for example, you are going to put 12 centimeters squared. Right? The cross section needs, like, if it's 30 by 60, that is enough for RC beam, for example. You are going to say, no, I'm going to make it 30 by 65 or 70. So this is overstrength you are putting. Similar situation whenever that you provide a minimum control design. All the minimums, you are providing extra overstrength for the system or the element. Finally, the design of many flexible structure systems like moment resistant frames often is controlled by the drift Yes, it is controlled by drift rather than strength limitations, especially moment resisting frame. This means what? That your strength is not going to be used. I mean that if you design for a limit of 100, for example, or 1000 kilonewton or something, you are going to find that there is another limitation would control your system to reach even this 1000, which is the drift control, the stiffness control. Okay, so this is why that's the point, that the drift is going to control, especially for moment resisting frame, going to control the design strength limitation of the standard with sections selected to control lateral deformation rather than to provide specified strengths. That's right, because we have some limitation for the drift for the moment resisting frame. So based on this, we are going to put this limitation. So these are the sources. So if I'm going to ask you what are the sources of overstrength, then you can tell me that we have 4 main sources of overstrength, and you can list these 4. Okay, overstrength of material, member design strength reduction factor, designer safety factors, and finally the stiffness controlling of some elements. Okay, now let's talk about the full yielding of structures, which is, we said it is here. This is the full yielding of structures. The result is that the structures typically have a much higher lateral resistance than that specified as a minimum by the provisions, and first significant yielding of structure may occur at lateral load level that is 30 to 100% higher than the prescribed design forces. That's right. Here, this is the prescribed design forces. Here it is the maximum one, from 30 to 100% higher. If provided with adequate ductile detailing, redundancy, and regularity, full yielding of structure may occur at load levels that are 2 or 4 times. Can you imagine 2? Means that 200% or 400% higher if you are making good detailing, redundancy, and regularity. Okay, so this means that it is something that we have our structure to be, yes, they are overstrength already. Okay, now let's go to the next one, which is what is the use of overstrength factor. Most structures, structure systems have some components that cannot provide reliable inelastic response or energy dissipation. That's true. In your structure system, you are going to find that you have some structures or some elements of the structure. They are not able to provide the energy dissipating pattern, or they are not going to provide a reliable inelastic response. So they need to be elastic. They cannot behave inelastically. Such components must be designed considering that the actual forces in the structure will be larger than those at first significant yield. That's the meaning here. This is the first this is the first significant yield, and we need to be, actually the meaning of this sentence, the meaning that we need this element to be elastic. That's it. We do not want this element to be in the inelastic range. It cannot work inelastically. Therefore, an overstrength factor is specified to amplify the prescribed forces for use in design of such components. Yes, that's right, especially if the components are important, like columns or collectors that is connecting between, or they are receiving some discontinuous walls, for example. This means that these are important elements and we cannot rely on their inelastic behavior. We need them to be responding elastically because we are a little bit worried about them. This specified overstrength factor is neither an upper nor a lower bound. It is simply an approximation specified to provide a nominal degree of protection against undesirable behavior. Okay, so this is the main philosophy of the overstrength factor. What we are going to do, what we are going to do with the overstrength factor, which is this one. We are going to use it here. that we are going to say that some elements should be multiplied, their load combinations or their loads should be multiplied by the overstrength factor in order to keep them, design them for forces higher than what the real structure is going to have from the design, so that they are going to be maintained elastic. Okay. Now, where this can be found in the table, we are going to find that this overstrength factor is here. For different lateral system, you're going to find it in table 12.2-1. It is almost like 2.5 or 3 for most cases, 2.5 or 3. And we said before that we can reach to like 4 times. Okay, we can reach 4, factor of 4. Okay, but anyway, that's what is given in the code. It is maybe 3 here. This is for only this systems. We have many systems. Okay, so you can't check them in the code. Now let's talk about the response modification factor, which is R. We're going to talk about R, the response modification factor. Okay, where is this response modification factor? Okay, this is the response modification factor. That is the relation between VE, which is V elastic, okay, V elastic. Let's go to the V elastic and the VS, which is the V at the design level. So this is the difference, the response modification factor, the elastic behavior. So what at this point? It is the elastic response of structure. Actually, suppose if we are going on the ADRS format, or in the if we are in the ADRS format, this is the acceleration displacement response spectrum. Okay, this is the capacity curve, and this is the demand curve. Okay, so you are going to find that this point is the intersection between the T here, which is the as if the unlimited elastic response of the structure. This is the connection, that if the structure was behaving elastically, unlimited elastically, then it would have deformation equal to this value, which is delta E. Okay, and from here we say that if we have enough ductility, we can assume that this structure is behaving under the elastic rule, the equal displacement rule, which is saying that the structure is going to behave or going to attain the same deformation under elastic or inelastic response. Anyway, this is a little bit advanced. I'm going to talk about it later, okay, in the ADRS format. But now I want you to understand what is the meaning of response modification factor. It is the ratio between the maximum base shear that could be attained by the elastic system if it works unlimited elastic, or if it works or behaves elastically without a limitation here, and the real design force. This is the difference. Okay, this is as if it is elastic, the system is elastic. Here it is based on our design. So the main purpose of R is to reduce the seismic demand on the structure. So we need to reduce the seismic demand. Okay, why we need to reduce, and why? What is the main reason? Let's read here, and I'm going to tell you about this. This reduction is possible for a number of reasons. So actually, the force that is coming from the earthquake need to be reduced. Why? Because the system is going to change during the earthquake. The system is going to be changed during the earthquake. There are two main things that is going to done. The T of the system is going to be changed to be T effective. It was T natural. It is going to be changed to be T effective, because there are plastic hinges are going to formed. So instead of Tn to be 1 second, for example, T effective is going to be 2 or 1.2 second. So there is increase in T. Increasing the T means that the response spectrum is going to do what? Yes, this is T, and this is the spectral acceleration. If we're increasing t, this means that t was here, and then if it increased, so it will be here. So this value is going to be reduction. Spectral acceleration is going to be reduced. Another thing is there is energy dissipating, energy to be dissipated through the plastic hinging, through the hysteretic damping. Okay, so we have two main sources here. First one is the effective period, okay, which is going to be higher than the original period of the structure, result in reduction in strength, as I have mentioned here. This is the philosophy of reduction in strength. Furthermore, the inelastic action results in significant amount of energy dissipating or energy dissipation through hysteretic damping, in addition to other sources of damping present below significant yield. The combined effect, which is also known as the ductility reduction. So this is what we call a ductility reduction. What is the meaning of combined effect? Of the effective long period and the energy dissipation. These are the two effective reasons. We combine them, and the ductility reduction concept explains why a properly designed structure with fully yield strength, V yield, which is here, that is significantly lower than the elastic seismic force VE. That's right, this is VE here, and this is V yield. This is the theoretical elastic behavior, base shear. This is the fully yield nonlinear behavior, base shear. Can be capable of providing satisfactory performance under the design ground motion excitation. Okay, so now you understand why this reduction. Okay, so actually from here to here, this is what we call it. There is reduction factor, which is VE over V yield. But from VE to VS, this is the response modification factor. So this is why in the codes you are going to find R, because we are designing at this level. But what the structure really is going to behave, it is going to behave like this here. Okay, so there is a kind of reduction from the theoretical elastic and from the real fully yield response by this amount. Okay, this is the reality. But this distance from here to here, this is because of the design. This is the code design. This is what we are having the design for. So this is why we put or we use RD. But the real reduction is going to be between the VE and V yield. Okay, now let's go to the next, which is role of engineering judgment. So we need to put what should we do for this. Actually, sometimes R need to be assigned, or you need to assign lower R, okay, than what is really there. For example, lower values should be used for structure possessing low degree of redundancy, wherein all the plastic hinges required for the formation of a mechanism may form essentially, yes, look to this word, simultaneously. Do you remember in the previous paragraph or previous slide I mentioned about sequential plastic hinging? Here it is simultaneous plastic hinging. So if the system is lacking of redundancy or have poor redundancy, and the plastic hinges are going to be formed simultaneously, okay, then in this case R should be small. So this is very important. So in this case we are going to find the code is providing something called redundancy factor, R. Okay, you are going to find that there is something related to the redundancy we're going to talk about this. This situation where that the redundancy and simultaneous plastic hinging is going to be at the same time, this situation can result in considerably more determinantal P delta effects. So P delta is going to be controlling here. Since it is difficult for individual designers to judge the extent to which R factors should be adjusted based on the inherent redundancy for their designs, There is a section in ASCE, which is section 12.3.4, provides a coefficient for, yes, the redundancy that I was talking about, that is calculated based on the removal of individual seismic force resisting elements. I'm going to talk about this. Okay, so this means that you need also to think about the R, the response modification factor. Okay, so we should choose this R with great care. So the designer should choose it with a great care. Do not follow blindly the code factors, but maybe you can put less or lower reduction or R factor based on your case, based on the design case and the building situation. Okay, now we have like the energy dissipation part, which means that we are having different types. The structure is going to dissipate the energy through what? Through the hysteretic energy of the members. Through the hysteretic energy of the members through several cycles. These cycles are due to the earthquake, okay, earthquake reversals. Some structures have far more energy dissipation capacity than others, and this is based on the detailing of the connections, for example, and the elements. The extent of energy dissipation capacity available depends largely on the amount stiffness, that's important, and the strength. These are the main two factors that is going to control the energy dissipating or the energy dissipated through during the cycles of the earthquake. So it depends on stiffness and strength degradation. The structure undergoes as it experiences repeated cycles of inelastic deformation. Let's have a look on here. So actually this is two systems for beam column component. This is a beam column assembly. The relation is between horizontal force and the horizontal deflection of the assembly. We found that two systems, both of them are beam column, okay? Beam column assembly connection. But one is having a stable kind of hysteresis loops, and another one is having a pinged one, as if it is pinged from here. Well, what is the point here? If you look to the slope of all of these cycles, you are going to find, look, the slopes are almost what? Parallel. This means that the stiffness, which is K, for all the cycles almost the same. And look to the strengths, you are going to find that the strengths almost, they are okay, degrading but not very high. It is okay for the system itself to say that this is stable hysteresis loop. This is the backbone curve, as you can see. The area inside, it is the area dissipated. The area inside is the area dissipated, because we have, whenever that we have inelastic system, for example, the system goes like this, okay, and then whenever that it yields or do some kind of nonlinearity, then the load for the return is different than the load, the path of the return is different than the path of the loading. So it will come from here, for example. Okay, so the difference between the two areas, so we have this area, which is the total area here, and this area, which is the area under the returning path. The difference is going to be this area, which is in between. Okay, so this is the dissipated energy. Okay, if this backbone curve is not like this, if the backbone curve, for example, it is going to be something like this, okay, then you are going to find that the area dissipated is less, and this is what is happening in the pinch here. So you're going to find that, look here, this is the backbone curve here, here, okay, and then it goes like this. This is okay, but you are going to find that this is the behavior here, the backbone curve. Okay, it is less. If we have something like this, this would be better, wide and open hysteresis. So we lost this part and this part, but here it is okay. Actually here, because take care of this of the scale, maybe the scale here is small, here it is big, but actually this area, which is inside the hysteresis here, is much less than this area. Okay, but take care of the scales only. Okay, this is 40 here. Okay, and we have -4 here. This is 30 here and -3 here. So you can imagine, I should have like put them in the same scale, not like different scales like this. Okay, I think this is the end of our part related to the energy dissipating. Let's go now to the redundancy, which is the another topic under our video for today. So the last part actually, which is going to be the redundancy. For the redundancy factor is intended to quantify the importance of redundancy. What is the story of this redundancy? The desirability of redundancy, or multiple lateral force resisting load path. This is the definition of redundancy. Multiple, exactly. In one sentence, it is being given for us. Multiple lateral force resisting load path has long been recognized, and the redundancy provisions of this section reflects the belief that an excessive loss of story shear strength, that's the point that we are taking care of, or development of an extreme torsional irregularity, the second point that is important for us, may lead to structure failure. So we are afraid of two things, which is shear strength and torsional irregularity. Why? Because they are going to lead to structure failure. So how we can control this? In ASCE, there is redundancy factor, which is going to take one of two values, 1 or 1.3. So if the system is lacking of, not lacking, it has redundancy, but we have some members that is carrying more than 33% of the shear strength, then we are afraid. We are going to be afraid. So we're going to design all other components with extra load, extra horizontal load by 30%. Okay? So whenever that, you can think about it like if we have, I want some, yes. For example, if you have like a city, we have two cities. City, it's a place, okay? Town, right? Town. And the first city, we have 3 main streets, okay? 3 main streets. And a second city, we have like 10 streets. The 3 main streets here carries almost like here 30% of the traffic loading, everyone 30%. If one of them is broken or not working, then the traffic is going to go to the other 2, right? But huge traffic would be there because it is 15% of the total percent of the traffic would be passed to the other 2. So this is dangerous, right? You're going to find that these streets, they are highly congested and we need to take care of them, right? But what about this one? We have like 10 or 12 streets. If there is a problem in this street, for example, if we have a problem here, do you think that there would be a traffic congestion in the other streets? The answer is no. Here, the forces or the traffic, it is the same, can go here and here, or here, or here, or here. It is okay. You have multiple paths. You are redundant. Here, you are not. The problem is if one element is taking more than 33% of the traffic or 33% of the load shear strength, then we need to be careful. We need to design the other 2 lanes or the other streets with 1.3. We are increasing them by 30%. So this is why in this case we are going to assign redundancy equal to 1.3. However, if this is the case, it is redundant and all elements does not carry more than 10%, for example, of the total traffic, then there is no need for the increase of the components, the other components. So we're going to use only 1 redundancy, 1. Okay, so did you understand the rationale of redundancy? Remember it with the street analogy that I have explained here, and it will be very easy for you to remember. And now, yes, this is the redundancy provisions of this section reflects, as we said it before, okay, reflects the belief that yes, because we want to avoid what structural failure, which is coming from extreme torsional irregularity and shear strengths, story shear strengths. Okay, loss of story shear strengths. We are afraid of this. So the traffic's example or analogy applies well here. The shear strength or the force need not to make any troubles for our structural system. Okay, we have, as we said, we have two values, and I explained them why. Okay, so the main reason for this, how we can judge whether our system is going to be 1.3 or 1. The point is, if we remove this element, the individual element, from the lateral force resisting system, is it going to cause the remaining structure to suffer reduction of story strengths of more than 33%, or creating an extreme torsional irregularity? This has provisions in the code. So if the element is going to do one of these two things, then we are going to apply 1.3 for the entire elements, for the all components, because the redundancy, it is applied in all directions, so this direction or this direction. So if we have redundancy here equal to 1.3, this means that all the resisting elements, lateral resisting element and components in this direction should be designed with load combinations having rho equal to 1.3. The redundancy factor is determined to be 1.3 in one direction. It applies to all connections and components in the structure that are designed to resist seismic loads in that direction. Okay, so remember, rho, it is not only for one individual element. It is for the all elements in the lateral resisting force system, okay, that is going to be as alternative path. Okay, they are going to work as the other streets for this element. Okay, so this is the meaning of redundancy and when we can use it. Okay, this is only two shapes that you can look to them. Whenever that we have, this is moment frame here, everywhere that is connecting between the columns, and in the periphery there is moment frames. This is a very high redundant system, because if this element is not working, then the loading is going to be distributed in many other elements. If this is not working, then there is some other elements is going to carry. But what about this system? If we remove, for example, this is special moment resisting, special concentrically braced frame, it is here. If we're going to remove it, or we are going to remove this one, for example, the system is going to be, or this one, the system is going to be irregular directly. Okay, if we are having the load from this direction and we remove one of them, it's a problem. It's going to be a problem. So this system B is not so redundant building, but system A, it is highly redundant element or building. Okay, you are going to find the redundancy in the code under item 12.3.4.2. You can read it here. It is actually, as I said, we are dealing with cases where that we need to avoid extreme torsional irregularity. Are going to find this, and there are some exceptions for this. It is not the scope of this video to discuss in detail about the redundancy. Okay, so actually this concludes our video. Yes, this is the redundancy. I'm sorry, this is 12.3.4. This is the definition of it in the code, and this is whether that it is going to be 1. And there are several cases where that the redundancy is going to be 1. The important things here, the important exceptions where that rho is going to be 1 is the drift calculation and the P delta effect. No need to take rho equal to 1. And also for design of non-building or design of non-structured components, no need, only rho, it is going to be 1. And this is logic because they are not part of the lateral resisting system. And drift calculation, it is drift. It has nothing to do with the shear strength. P delta effect also, it has nothing to do with it. Okay? So whenever also we have some cases where that overstrength is going to be used in the combination, no need to use rho also. Rho should be 1. It will not be 1.3 in this case. That's it. And there are other actually exceptions, but it is not the scope of this video. I'm going to talk about redundancy in another video later on, because it's very important and we need to check what are the ways, because we have two different approaches for checking the row or the redundancy, but it will be in a separate video. Okay, anyway, thank you for listening and see you in the next video.